Hi everyone. In this episode, we will discuss a block cipher called the fiestal cipher. These are the contents: stream cipher and block ciphers, motivation for the fiestal cipher structure, fiestal cipher, diffusion and confusion, and the fiestal cipher structure. Stream cipher. In encryption, we are converting a plain text into ciphertext. If it is done one bit at a time, it is called stream cipher. Examples are additive cipher, monoalphabetic cipher, and beginner cipher. See this block diagram. In this, the bit pi of the plain text, it is used with the bit ki of the key and converted into ciphertext ci. And again at the decryption side, the ciphertext bit ci and the key bit ki is used to give back the plain text. Next type is the block cipher. In this, the plain text is converted to ciphertext in blocks. That is, one block of data is taken and that is converted to the corresponding ciphertext. Similarly, next block of data is taken. Instead of bit by bit, it is done block by block, and the number of bits in a block is fixed. For data encryption standard DES, the block size is 64, and another algorithm, advanced encryption standard AES, the block size is 128. Now we can see what is the motivation for the fiestal cipher structure, or why we have applying this type of cipher. It is a block cipher which operates on a plain text block of n bits to produce a ciphertext block of n bits. So the advantage here is, if a block has n bits size, then there are 2 raised to n possibilities for ciphertext. And here in the plain text to ciphertext mapping, there are 2 types of mapping. One is the reversible mapping and next is the irreversible mapping. Reversible means once we convert from the plain text to the ciphertext, we should be able to convert back. That is, from ciphertext, we should be able to identify the plain text. For example, if the bit size n equal to 2, then we have 2 raised to 2. That much possibilities we are having. That is 4 possibilities: 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 plain text is mapped to 1, 1 ciphertext. 0, 1, 1 mapped to 1, 0, 1, 0 mapped to 0, 0, 1, 1 mapped to 0, 1. Irreversible mapping means from ciphertext we cannot come back to the plain text. We can see the example for irreversible mapping, which is, so this plain text is given as 0, 0, 0, 1, 1, 0, 1, 1, and ciphertext is also given here. So here we can find that same ciphertext we are having more than one plain text. That is, the ciphertext here for 0, 1 and this plain text is 1, 0 is there and also 1, 1 is there. So while converting back the ciphertext to plain text, if we cannot identify 0, 1 indicates either 1, 0 or 1, 1. But in this reversible mapping, 0, 1 means only 1, 1. So that is the difference between reversible mapping and irreversible mapping. For an ideal block cipher, it can have 2 raised to n factorial number of different transformations. If n value is small, that is number of bits in a block is small, then it is easy to identify the plain text from the ciphertext. So it is vulnerable to statistical analysis. So ideal block cipher is not that much efficient for encryption. So fiestal made some approximations to this ideal block cipher and made his own cipher structure called the fiestal cipher structure. So in this block diagram, we can see that 4-bit input, which is a plain text, it is given to a 4 bits means 2 raised to 4 possibilities are there, which is 16 possibilities are there. So we are using here a 4 to 16 decoder, and then at the other end, while producing the ciphertext, here we are using 16 to 4 encoder, and 4-bit output is produced. Fiestal modified the ideal block cipher by using the concept of product cipher. Product cipher means it uses substitutions and also permutations. Substitution, permutations here means transpositions. So a combination of substitution and permutation is used by the fiestal cipher. It also uses the functions confusion and diffusion. Diffusion is a technique used to hide the relationship between the plain text and ciphertext by spreading the plain text digits over the ciphertext digits. But confusion is a technique to hide the relationship between the ciphertext and the key. Fiestal cipher structure. We can see the fiestal cipher structure in this block diagram. So here the left side shows the encryption process and the right side shows the decryption process. So in this cipher, in all the ciphers, what we'll do is plain text is converted to ciphertext with the help of a key and the encryption algorithm. So this follows a particular method, some substitutions and permutations in order to provide more security from the attackers to identify the plain text from the ciphertext. So we can see this diagram. First, see here, this is the input plain text. This plain text, block of the plain text is divided into two halves. For example, if the block is of length 64-bit, it is exactly divided into 32-bit left side and 32-bit right side. So left side is shown here, left encryption. Then right side is shown here, right encryption, RE. So 0 means it is the first step, that is why it is starting from 0. Like this, 16 rounds are there in this fiestal cipher. Round 1, round 2, round etc. 3, etc. up to round 15, round 16. 16 rounds are there. And each round, the same process is repeated. So first round, the input is LE0 and RE0. So here in this approach, left side, we are not doing much with the left side bits. Right side, what we have to do is, we have to give the right side RE0, right side half, to a function f, which is called as a round function. And a key also is given, a sub key also is given to this function. Sub key K1. Sub key means it is part of the main key K. And then after that, the output of that is given to an XOR function. So this left half is given to this XOR. So output of this function f and the left half is given to the XOR, and then that output becomes the right half for the next round. The left half for the next round is the right half of the previous round. So this same process repeats. So once again we can see the plain text is divided into two halves, left side and right side bits. If it is 64 bits, it is divided into 32. Then left side, we are not doing anything much with the left side. Right side, we have to give to right side bits, we have to give to a rounding function, and a key sub key also provided to the rounding function, and the output of that function is given to an XOR with the left half of the plain text, and that output of the XOR is given as the right half for the next round. The left half for the next round is the right half of the previous round. Similarly, if we can see in the next round 2 also, same process gets repeated. Right side is given to the rounding function f with the subkey k2. Each stage or each round, the subkey is different. So this provides maximum randomness to this algorithm and maximum security. So similar to this, 16 rounds are there. After the 16th round, we'll be getting the left side as LE16 and right side as RE16. Then just one swap is done. That is, right side is swapped to left side and left side is swapped to right side. So this swap becomes after the swap, it becomes the ciphertext. So each stage we can make an equation. For example, RE1, the right half of the second round, how we have obtained that RE1 is equal to LE0, this one, XOR F of RE0, K1. Like that, this left half LE1 is equal to RE0. Directly RE0 we are giving. Similarly, RE2, how we are obtaining RE2? It is LE1 XOR F of RE1, K2. Similarly, each round has doing the same step. And finally, after the 16th round, we will be getting this LE16 left side and RE16 right side. Just swap that halves. So RE16 comes here and LE16 comes right side. So this becomes the ciphertext. And this is the encryption process. From plain text, after 16th round, we have got the ciphertext. Now we can see the decryption process. Decryption process means the ciphertext, we have to convert it back to the plain text. So since we are using XOR operation, XOR has some properties. So we can easily get back the plain text. So here input is the ciphertext given. Ciphertext means it is, so this side, left side is RE16 and right side of the ciphertext is LE16, that is given here. LD0 means the ciphertext left side decryption, LD0 first round. Then RD0 right side decryption. So this is also divided into two halves, and here also right side is passed to the rounding function with the subkey in each round with the subkey, and then XOR function. So similar to that, it's going on. So here this right side is given to this function and then with the key. This right side is directly becomes the left side of the next round. Then left side is XORed here. So same as encryption, the process is same, and at the end of the 16th round we will get the ciphertext. The ciphertext has to be swapped again to get the plain text. See the description for the block diagram. That is, first the plain text. The inputs to the encryption algorithm are a plain text block of length, say 2W bits, and a key K. The plain text block is divided into two halves, the left side L0 and the right side R0. The two halves of the data pass through n rounds. So in this example we have seen it is 16 rounds of processing and then combine to produce the ciphertext block. Each round I has inputs Li-1 and Ri-1 derived from the previous round, as well as a subkey Ki derived from the overall K. The subkeys Ki are different from K and from each other. In the figure, 16 rounds are used. Any number of rounds can be used. All rounds have the same structure, that is important. A substitution is performed on the left half of the data. This is done by applying a round function f to the right half of the data and then taking the XOR of the output of that function and the left half of the data. F is a function of right half block of W bits and a subkey of Y bits. F can be represented as F of REI, right side encryption, comma KI plus 1, subkey. After the substitution, a permutation is performed, which means the swapping of the two halves. The realization of the fiestal network depends on the following. First one is the block size. That is, we can consider the block size is 64, or key size, then number of rounds, then subkey generation algorithm, then the round function f. And here one thing we can notice, the output of the first round of the decryption process is equal to a 32-bit swap of the input to the 16th round of encryption process, which we can prove. We can prove that at each round of encryption and decryption, the values are same except that the two halves are interchanged. For example, consider this round. In this, LE14 and RE14 is at the encryption side, but this side it will be RE14 and LE14, that is right and left halves are interchanged. Similarly, every round it will be same. So at the end, in order to get the plain text, so here it is LE0, RE0, which is the plain text. So here it will be RE0, LE0. So after one swap of the two halves, we will get the plain text, which is LE0. This LE0 comes here and RE0 comes here after the 16th round of the decryption. So we have to prove this, that is at each stage the values are same except that the two halves are interchanged in each of the rounds. In order to prove that, we can consider one round. This example we can take, that is this one, LE15, RE15, and here it will be the output of round 1 of decryption, which will be RE15, LE15. That thing we have to prove. This is the input to the 16th round. This is round 16, and LE15, RE15 is the input to the 16th round, and this is the output of the first round of decryption. These two things are same except that the two halves are interchanged. That we have to prove. So in order to prove this, that is written here, show that the output of the first round of the decryption process, that means this is the first round of decryption, output of that round means this, is equal to a 32-bit swap. If total 64 bits means one half is 32-bit. So 32-bit swap of the input to the 16th round of encryption. So this is the 16th round. Input to the 16th round of encryption is this one, LE15, RE15. So 32-bit swap means RE15 goes here, LE15 comes here. That becomes this one. This thing we have to prove. So first we can consider the encryption side. From encryption side, we can identify that this LE16, what is LE16 from this figure? LE16 is obtained from this RE15. So that I can write down here, LE16 equal to RE15. Then what is RE16? How I will obtain RE16? I obtained RE16 by LE15 XOR F of RE15, comma K16. That I have written here. RE16 is equal to LE15 XOR F of RE15, comma K16. So that I have written down from the encryption side. Now I can see the decryption side. On the decryption side, this part I have to prove. That is, it is the swap of this one. So I will write the LD1. What is LD0 and LD1 means? LD0 means left side decryption 0. That is input of the round one. Then left side decryption. Again, this is RD means right side decryption. So LD1, I have to prove that this LD, this side is this one, RE15. So in order to prove that, I have to write down LD1. LD1, what is LD1? How I obtained LD1? LD1 I have taken from this side directly. So RD0. So I'll write LD1 equal to RD0. Again, what is RD0? So this is the ciphertext. So ciphertext, how I obtain the ciphertext? So this is the last round output, LE16, RE16. That one I have swapped to get the ciphertext. So ciphertext, this right side means this left side. This left side becomes the right side. So LE16. So RD0 is LE16. So that I can write down RD0 equal to, so LD1 equal to RD0 equal to LE16. LE16 from the previous round I know that it is RE15, so I can write down this. So we had to make it in terms of 15, the number 15, then only we can prove this stage. That is why I am bringing it to RE15, LE16 equal to RE15. So LD1, I have proved that it is RE15. LD1 means this left side of this decryption is same as the right side of the encryption. That thing I have proved. Now I have to prove for the RD1. So in order to that, I had to write the equation for RD1. How I have obtained RD1? RD1 equation I will write down here. That is RD1. This is the XOR of LD0 XOR F of RD0, comma K16. That I have written here, RD1 equal to LD0 XOR F of RD0, comma K16. This thing I have to reduce, and finally I have to prove that this RD1 equal to this right side equal to this one left side, LE50. So this one I will again expand, LD0. Instead of LD0, LD0 is this one. This one means this left side of this means this is the right side, RE16. So instead of LD0 I have written RE16. Then XOR I have written here. Then instead of RD0, what I can write? RD0 I can write, I had to bring it to the term of 15. So I can write RE15. RD0 is RE15. So I have written, instead of RD0 I have written RE15. Then comma K16 is written. Again, now I see this one means again this RE16 is there, that I have to bring into the terms of 15. So RE16, what I can write? See, instead of RE16, I can write LE15 XOR F of RE15, comma K16. So that thing I have written here. Instead of RE16, I have written LE15 XOR F of RE15, comma K16. Then again this XOR I have written. Then this same function I have written. F of RE15, K16 I have written down. Then some properties of XOR are there. According to that, I can deduce this. So one property is the distributive law, A XOR B XOR C equal to A XOR B XOR C, which is a distributive law. So I can apply the distributive law over this. So here this bracket is there, XOR this one. Instead of that, I can put the bracket over here. LE15 XOR, then I put the bracket. If I put the bracket here, for example, if I can, this one. If I put the bracket over here, LE15 XOR this one, F of REC 16 cases, and put the bracket over here. Then now since I can use the distributive law, I have distributed this one. This XOR, this bracket I have changed to this here. Then now I can understand that this will be LE15 XOR. Here I can see that both values are same. F of RE15, K16 XOR F of RE15, 6. Both are same. So both values are same. If you are XORing, there is another law of the XOR, another property for the XOR, that is D XOR D equal to 0. So this becomes 0. This part becomes 0. Then what is remaining? LE15 XOR 0. Anything XOR 0 becomes that itself. So this LE15 XOR 0 becomes LE15 itself. So I have proved that RD1 I have expanded it, and I have proved that RD1 equal to LE15, which is required. That is RD1, the right side of the decryption, equal to the left side of the encryption. So I have proved that one. So this is one simple proof to understand that at each stage the encryption value and the decryption value are same, except that both of the halves are swapped or interchanged. This, and again here it is given one general formula for this one. Each round, that is LEI equal to REI minus 1, that is LEI, this one equal to previous round RE, that is RE0 here, LE1 equal to RE0, generalized and written here. Similarly, REI, how we can write REI, this one, for example, RE1, how I can write LE0, that is LEI minus 1 XOR F of REI minus 1 comma KI. So this is one general formula for this operations. Thank you everyone.